So, good morning, good afternoon, or good evening, according to your time zone. I welcome you to this seventh lecture of the online training series Observing Marine Ecosystem Structure and Function from Microbial Communities to Fisheries and Human Health. This is the virtual component of the in-person training course going to be held in India at the end of October, preceding the TREVOR Symposium. Apart from students going to attend the in-person course, this series is open to the whole marine research community and especially encouraged our students and early career professionals. Therefore, we're glad to see so many people today. Reminder, this is a lecture, so please take advantage of the knowledge of the speaker as well as the panelists and ask as many questions as you want. And please post them on the Q&A box and we'll get to them after the talk. So before introducing our speaker, we also have a panel that will help in the discussion. And it's composed by Dr. Shiva Sasiendranath, Senior Scientist at the Plymouth Marine Laboratory in the UK, Dr. Lilian Krug, Scientific Coordinator of POGO in Portugal, and we hope to get Dr. Rashdeep Roy here. He's a senior scientist at the National Remote Sensing Center in India. So now it's my pleasure to introduce our speaker today, Dr. Arvind Singh. He's an associate professor at the Physical Research Laboratory in India, where he utilizes stable isotopes to trace ocean biogeochemical processes. His research focuses on the ocean carbon cycle, nutrient stoichiometry, and the impacts of rising atmospheric CO2 on marine ecosystems. He has contributed extensively to understanding ocean acidification, marine nitrogen cycling, and emerging carbon dioxide removal approaches such as ocean alkalinity enhancement. Dr. Singh has worked with leading international research institutes, including Geomar Helmholtz Center for Ocean Research in Kiel. He's a recipient of the prestigious Swarnashayanti Fellowship from the Department of Science and Technology of the Government of India for his work in ocean-based climate solutions. And he's going to talk today about observations of marine biogeochemistry. And this talk will build up from our previous lecture on primary production. And Arvind will introduce us to ocean processes. So Arvind, the floor is yours.
Thank you. Thank you very much, Vivian. Thank you, Shubha. Thank you, Lika. And also thank you, Rajdeep, if he's around for this invitation. I think anything linked with TREVOR, it's an absolute honor to be part of that event. It is needless to say here in this forum, everyone is aware. However, I would like to still say a few words about this, and let me share my slides. Okay, so before we begin our seminar today, I would like to take a moment to remember these two remarkable scientists whose legacies are particularly meaningful for this particular seminar, as you know. So on the left, as you see, Professor Trevor Platt, in whose honor this seminar series has been established. And Trevor was a pioneer of ocean color remote sensing and biological oceanography, but his contribution went beyond his scientific discoveries, as we all know. And he had a remarkable vision for building scientific capacity, particularly for the developing countries, and for using observations and science to address larger questions about our planet. And on the right, I have put the picture of Professor Vikram Sarabhai, and he built a physical research laboratory and where I worked. So that is also one of the reasons that I put these two pictures together. And also, as you can see, the coincidence, both were born on 12th of August. So that is also another coincidence. And they were both institute builder or scientific capacity builder, and also has a lot of link to remote sensing, to satellite. For example, Vikram Sarabhai is also known a father of Indian remote sensing or Indian space research program. and both had a vision for developing countries. In Trevor, he worked quite hard for the scientists who work in the developing countries. Likewise, Sarabhai saw that any science that we do, it should be for the societal development. So he never saw the science and the societal development are two different things. He saw them as one, and that is how we see it. So this is indeed a great occasion for us to pay our tributes to these two pioneers or visionaries who have put the science where it is today, particularly the space and ocean science where it is. All right. So today's topic is about the observations of marine biogeochemistry, and I have slightly tweaked the title that I will tell you why did I tweak it, about the carbon and nitrogen isotopes in the biogeochemical cycling. So as you know that the ocean is constantly processing carbon and nitrogen. It is producing carbon and nitrogen, consuming carbon and nitrogen, and transporting them, and also transforming them. But most of these processes are invisible to us. We don't see them. So what if we could give these elements a fingerprint and then follow those fingerprints through the ocean? So essentially, these are the fingerprints that we follow, or rather the stable isotopes, they help us to follow these processes through the fingerprinting. And this is what we are going to learn in this particular talk. So today I want to talk about how the small differences in the abundance of carbon and nitrogen isotopes, they can tell us about some of the biggest processes in the ocean. Those are from primary production to nitrogen fixation to remineralization and the cycling of the organic matter. And like it's been already, Vivian has already mentioned it, that my talk is also somewhat linked to the previous the talk last week by Ryan, and he gave an excellent talk about primary productivity and discussed almost all kind of methodologies that is available. So it was a great talk. I learned quite a lot from that talk, and I'm sure you must have also learned that. So my plan originally was to explain primary productivity itself, but that has been already done. So that is the reason I have decided to go a little bit more deeper into the details about isotopes, the basics of isotopes, and how they are useful to understand the biogeochemical processes, and also touch upon some other elemental cycling processes, for example, nitrogen cycling processes, nitrogen fixation, NMOX, denitrification, and how do we learn them. So that is the reason I have planned it slightly differently, but also that talk by Ryan, it's been very useful, and I'm sure if you have attended that talk, it would be also it will be very helpful for you to follow my talk as well. And in terms of research or the uses of isotopes, this is where we stand right now. So we use these isotopic ratios in dissolved inorganic carbon, particulate organic nitrogen, nitrite, ammonium, N2O, biology, sediments in the biology. So all these are the samples that we use. And the processes that we understand from these isotopes are, they include photosynthesis and primary production, ARCs, carbon exchange, organic matter remineralization, carbon export burial, and then of course the other nitrogen cycle processes, for example, nitrogen fixation, denitrification, nitrate assimilation, new production, NMOX, these processes we understand. And then in a holistic way, we analyze these data which has come from isotopes and from these samples to make them into concentrations and rates and experiments, and also use molecular biology and ocean observations to understand all this. And then we applied them to understand the modern process studies. We try to understand the sources of these different elements in the ocean. And today I will not touch upon, but the isotopes are also quite useful in paleoceanography and paleoclimate studies. And also we can understand the impact of anthropogenic activities in the ocean by these isotopes. So like I said in the beginning, they have their these processes have their fingerprints in the form of isotopes that we analyze. So our current understanding, if I can summarize, it is that the carbon and nitrogen isotopes are powerful tracers that help quantify marine biogeochemical processes, sources, and sinks, and their variability across space and time. But before we go into the too much details, I thought it would be a good idea to understand the basics of isotopes. What actually are isotopes? What are, for example, isomers? So the isotopes are nothing. It's the same element, but has different masses. So these are different versions of the same element. So they are identical in protons, and protons are normally defined by Z. This is the nomenclature that we follow, and X is the element here. So for any element X that we write, something that is in the left hand side subscript is Z, and on the top we write A. So A is nothing but the mass number, which is nothing but the sum of neutrons and protons. So these are and these isotopes, they have identical electrons. So the two isotopes of an element, they have the similar number, same, not similar, but exactly the same number of protons, different number of neutrons. And also because the proton number is same and they are not charged, so they have the identical electrons. So because the electrons are same, the chemistry of the isotopes remain exactly the same. So for example, if you react CO2 with water, you form carbonic acid. It doesn't matter whether this whether the carbon was carbon 12, carbon 13, or even 14, or whether hydrogen was hydrogen 1, hydrogen 2, or hydrogen 3. It doesn't matter. The reaction would proceed in a very similar way. So, and this is because the number of electrons remain the same. But because their mass is different, the number of different neutrons, they make the mass different. The physics changes because physics depend on the mass. So the amount of energy that you give to different isotopes, their behavior would be very different. And this is the property, these two properties, that the same chemistry, difference in physics, these two properties we use to understand different processes. So in a nutshell, the isotopes are nature's way of giving the same element different weights, literally, and scientists use those weights to tell the stories about the past and the stories about the modern ocean as well. For example, if you take carbon isotopes, so as we all know, carbon has three isotopes: carbon 12, carbon 13, and carbon 14. However, today we are dealing mostly with the stable isotopes. So that means with time, their abundance does not change. So carbon has two stable isotopes, carbon 12 and carbon 13. So again, this is the mass number, and the atomic number is 6 for both of these. And by definition, the atomic mass of carbon 12 is 12 AMU, atomic mass unit, and carbon 13 is 13.003. So up to this much precision we can go. And their mole fraction abundance is 0.988, and as you can see, it goes to several decimal places. And this is not just not the mathematics, but this also has a meaning that we will learn in coming slides, that why are we keeping so many decimal places and why are we not rounding off. And carbon 13 has a abundance of 0.011, and if we say in percent, then just we multiply by 100, so this becomes 98.89%, and this is 1.10%. So together it is 100% because there is hardly any carbon 14 in the system. And if we look these, so for example, from here you would have seen it's mostly up to 99% is carbon 12. The heavier isotope has very low abundance. And this is true for most of the isotopes, barring a few isotopes, that the heavier isotope would have a lower abundance. For example, here, these are the stable isotopes traditionally that we use in oceanographic studies, and we will come in detail about primary productivity. Again, we will not go back to the top, we will not run away from that topic, we will come back. But for the sake of completeness of this talk about the stable isotopes, let me also try to explain some other isotope systematics. So for example, hydrogen, the minor isotope, minor means the one which has less abundance. It is deuterium, which has 0.01. and carbon 13, as we saw, 1.11%, nitrogen 15N is 0.36, and because the most abundant isotope 14N, that would have more than 99% of the abundance. And the yellow part that you see, that we are having so many of decimal places, as I've said, the information actually lies in these decimal places. The changes that happen naturally, although they are stable isotope, I must make it clear. However, their abundance does change in the nature, but the change happens in these decimal places, fifth to sixth decimal places. The changes happen at times. Sometimes it can also happen to fourth decimal place, and because the change happen at so many decimal places, after so many decimal places, it is uh, it is not appropriate to report these numbers. So rather we report the isotopic values in a notation called delta notation. And delta notation is nothing but the R sample. So that means we don't just report the abundance of a particular isotope, rather we report in terms of a ratio. So this ratio R would normally be ratio of a heavier isotope to a lighter isotope. In case of carbon, for example, the ratio would be 13 carbon divided by 12 carbon. And then we have to have a reference because we want to see how much it has changed. So there must be a reference for which the isotopic values or the isotopic composition does not change. And then for the deviation, you of course you subtract 1, and then we multiply by 1000. And this is again because this number would out to be very small. So rather than multiplying by 100 and making it per percent, we multiply it by 1000 and report it in per mil. So per mil means per thousand, so that the number becomes somewhat meaningful. And as you can see, this is the systematics, for example, hydrogen, lithium, boron, carbon, nitrogen, oxygen, chlorine, sulfur, and all these ratios, absolute ratios, are listed here. So these ratios, barring boron, because for boron it is slightly different. The heavier isotope has slightly higher abundance in nature. And for all the other systematics, the ratio goes to 10 to the power minus 2 or 10 to the power minus 4, something of that range. And then of course we do. So we define a delta value. For carbon, it will be delta 13C. For nitrogen, it will be delta 15N. And like I defined before, and in terms of delta notation, the delta 18O would become 18O by 16O of the sample divided by 18O 16O in ISMO, that is the sea mean ocean water. That's a reference for which the isotopic ratio does not change. And by definition, the delta 18O value of the ISMO would be absolutely 0. And then you multiply by 1000. So this is what we do. And if you look at the natural abundance of or the natural ratios of these isotopes in different systematics or different reservoirs, for example, if you look at the ocean water or fresh water, and if you look at the 17O ratio or 17 ratio or 18 ratio, so 17R means 17 by 16 in water, 18R means 18 by 16 in water, and these are the ratios which are presented here. And in the ocean water and in the fresh water, there is a slight difference. So the question is, while being the stable isotope, being the stable, why does their abundance changes? So their abundance changes because of natural processes, because you give some energy to to molecules, and by giving the energy, their behavior changes, and their behavior, because their behavior depends on the mass. And this is something which is called the isotope fractionation. So because of the isotopic fractionation, their values in different reservoirs, for example, in oxygen composition of fresh water and ocean water, the carbon isotopic composition of the marine phytoplankton and the terrestrial plant, and the DIC, the dissolved inorganic carbon, which is present in the ocean, they are all different from each other. They are not very different, but they are different to the level that we can measure in the lab and we can understand the processes. And the question is, why do isotope fractionate? So the isotopes, they fractionate because the energy that is required to break the bond of heavier isotope and the lighter isotope is very different. For example, in case of H2, that is DD, deuterium, and when you have H2 in the form of 2H2H, and H2 in the form of 1H and 2H and 1H and 1H. There is something called 0 point energy, that is the energy required to break the bond, and that depends on the vibrational frequencies of these diatomic molecules, and that is quite different. That is different for different molecules, although they are the same molecules. That means the elements are same, but the isotopes are different. And for molecules we call them isotopologues. Like for element you call isotopes which have the same atomic number and different mass, and for molecules which are the same molecule but have a different mass, we call isotopologues, because the system works in terms of molecules, not in terms of atoms. When the phytoplankton take, they do not just take the carbon, they take the CO2, so they work as a molecule. This is the reason. And then the molecule, whether the molecule is made of heavier isotopes or lighter isotopes, the energy to break this bond, that would be different, and for the given amount of energy their behavior would be different, and this results in isotope fractionation. And this is the reason, and this is a very useful thing, this isotope fractionation. This is the reason we are able to use these isotopes to quantify the important ecosystem elemental cycling pathways, for example primary production, and also we can identify the sources. So first I will talk about the cycling pathways or measuring different metabolic rates in the ocean, and then if time permits I will also discuss more about the how do we identify the sources of different nutrients to the ocean as well. And we use this property of isotope fractionation as a tool, particularly for the second one, isotope fractionation, and for the first one, because their abundance is low, so we use them in different ways. So before we move forward and learn the technique, how does it work, let us revise our understanding of primary production and nitrogen fixation. So for example, primary production is the conversion of inorganic carbon to organic carbon anywhere. In for marine primary production, it is the conversion by the mostly by the phytoplankton in the ocean. They take carbon dioxide, and then this becomes the organic carbon in the ocean. And primary production by definition is a rate, so you have to have a time unit in a given time, how much CO2 is converted into the organic matter. That is what we call primary production. And this primary production, as you know, it depends on the nutrients, availability of the nutrients, particularly nitrogen and phosphorus nutrients, that determines the primary production in the ocean. So if I can summarize the equation, this is what the equation of primary production would look like, that some given amount of carbon dioxide would be fixed to become organic carbon, provided you have some nutrients present in the water. And of course there is plenty of water in the ocean, so that we don't have to worry about. So ultimately this, and if we can still assume that the red filled ratio is valid in all kind of forms or in all kind of reservoirs in different places in the ocean. So that is a big assumption, because now we know that there is a change in the red filled ratio, but for our talk we can assume this to be true. Then even by, if we can calculate that how much nitrate is being taken up by the phytoplankton, we can also convert that how much CO2 they would have fixed by this stoichiometric ratio. So we can use the isotopes of carbon, isotopes of nitrogen, or the isotopes of phosphorus to track and also to estimate the fixation of CO2 by the marine organisms. So these are the techniques that we all know. There is a technique based on radioactive isotopes, and also because you would produce oxygen in the primary production. So if you can measure 18O isotope in there as a production, that would be one ways. Or we can measure 15 nitrate, 15 ammonium, or 15 urea uptake, because these are the predominant form of nitrogen, or rather the bioavailable nitrogen that are present in the ocean. Or we can label our samples with carbon 13. That would also be one way. Or we can utilize phosphorus isotopes. For nitrogen it could be the 15N2. So N2 fixation is slightly different. So N2 fixation is the amount of N2 gas that is being fixed, and this is done by the special type of marine species called disotrops. By definition, they fix N2, and they require certain other kind of nutrients to fix N2. And for N2 fixation is slightly different. So for that, we require 15N2 gas as a tracer to track the pathways and also to estimate the amount of nitrogen fixation. And this something that is I have highlighted. These are the techniques that we will learn in detail in this particular talk. The other techniques I will leave, and this is mostly deals with the use of stable isotopes. So the tracer technique basic idea is that the small amount, as we have already seen, the heavier isotopes, they are present in very small amount. Their abundance is quite low. So the small amount of heavy isotope given to the substrate pool, it can be traced to the product pools. And it allows direct observations of transport and uptake of various compounds, for example, carbon. And the method to identify and quantify transformations by means by which we make the direct measurements. So it is not just the measurement of the concentration, rather we can directly estimate the rate of carbon fixation and rate of nitrogen fixation in these. But there is a big assumption that we have already learned these isotopes fractionate. So in this particular cycling pathways where we estimate the rates of carbon fixation and nitrogen fixation, we make a big assumption that the biological uptake of labeled carbon or labeled nitrogen, it is proportional to the biological uptake of carbon 12. So that means the biology does not discriminate between carbon 12 and carbon 13 or nitrogen 14 and nitrogen 15. It takes them in the same way. And up to some extent for our labeling experiment, so these are we call the tracer based studies. For these kind of studies, it would be okay because we add them into certain high amount where the fractionation in our estimates would not matter quite a lot. That would be within the uncertainties of the measurements that we normally report. And again, the basic idea for carbon 13, if I take an example, then the natural abundance of rare isotope is low. So the transformation of label can be traced above background. So for example, carbon 12, as we learned, it is only 1.11%. If you label it up to 99%, in terms of if you add sodium bicarbonate, which has carbon, if this is taken up by the phytoplankton, it will be immediately reflected in the particulate organic carbon. So that is what we do. So for example, in carbon, the natural abundance is roughly 1% here. So in the particulate carbon also it is 1.07%. So don't worry, sometimes it is reported 1.11, 1.00 or 1.10, but it is close to 1%. And but because in the these are called the enrichment experiment, enrichment tracer experiment, we artificially add carbon 13, which is 99%. So we add that 99% bicarbonate in here, and then but the in the organic matter body or even in the form of dissolved inorganic carbon in the water bottle, it would not become 99% because there is some carbon 13 already present. So there will be a mass balance. So it would not be 99%, but it can go up to 10%. Or rather, this is what we try to do. We do not want to interfere with the system too much that it can change the natural abundance, or rather the natural concentration of DIC quite a lot, or concentration quite a lot. So just to tell you, in the ocean, how do we do this experiment? So with the CTD rosette sampler, you collect the water samples, you bring them on the deck, or you can also, anyway, you will have to bring them on the deck, and then you add the tracers. If you want to measure nitrogen fixation, add 15N2 gas. If you want to measure primary production, in this case, we add carbon 13, and then you incubate. There can be two kind of incubation. Some people also do in situ incubation. That means you drop the bottles in the ocean from which depth you have taken. That is one way. The other way is you can do the deck incubations and provide the sunlight, the natural sunlight, which is there. and then you give them time, because you want to measure primary production. You have to give them time for the phytoplankton to consume some of the nutrients that you have provided, or the organic or the inorganic carbon that we have provided, and also to see that tracer, whether it has gone to the body of these phytoplankton. And then after some time, normally it is recommended that we do 24 hours of incubations, and after those incubations we filter them. So all our organic matter, all the phytoplankton, they are on filter. Normally we use 0.7 micrometer of size filter, and then you preserve them, you bring them to the lab and then analyze them and do the uptake calculation. I would also, because our topic is about the stable isotopes, I will discuss in detail about the analysis part, that how do we analyze them. And also this is how the experiments are conducted on the on the deck of the ship. We do like this. In case of nitrogen fixation, we have to add the tracer in such a way, because this is a gas, so this should not leak out, and you should add in such a way that this happens. So this is for a bubble method, but there is also another method called dissolution method that we normally use. And the analysis part, how do we do this in the lab? So in the our sample will be the glass fiber filter. And the reason we take glass fiber filter, because we do not want any carbon and nitrogen in our filter, because otherwise we would analyze that. So that's the reason we use this glass fiber filter. And on our filter we have particulate organic carbon, particulate organic nitrogen, and even phosphorus, or there can also be other biogenic silica, there can be other stuff. For today's discussion we are mostly focused on carbon and nitrogen. So this is in the solid phase, and ultimately this would go to mass spectrometer. Now the mass spectrometer analyze the gases, it cannot analyze the solid part. So that means our sample, we have to convert it into the gases. So for that we do the something called combustion at a very high temperature, up to of the order of 1000 degrees centigrade. And there would be some oxidizing agent, for example chromium oxide in there. So we would put our sample here, we burn it at high temperature. So there will be production of oxidized gases, for example CO2, N2O, these gases. And then we would want, for example N2O we do not want, we want in the form of N2. So for certain gases we want to do the reduction. So this is called the oxidation chamber. And then we have the reduction chamber, where the temperature is slightly lower, and then we put this reducing agent. For example, in terms of in here it is the copper, reduced copper, so it will reduce those gases. And then it will pass through a water trap, or rather this magnesium percolate. This will trap what we do not want any water to go inside the mass spectrometer. So we will trap the unwanted things here, or the water vapor here. And then this would go to IRMS, which stands for isotope ratio mass spectrometer. Actually, any kind of mass spectrometer is isotope ratio mass spectrometer, but the mass spec that we use for carbon, hydrogen, nitrogen, sulfur analysis, somehow the name is also given isotope ratio mass spectrometer, in which also we pass the CO2 gas. Because if you remember the isotopic composition formula, we measure these isotopes with reference to a gas. So for example, for carbon it should be a CO2 gas, for nitrogen it is the natural air, which has already 78% of nitrogen, so that we put. And then also there is a carrier gas that we require, so here we put helium. So our carrier gas should be inert, it should not react with our sample. So that is the reason we use helium as a carrier gas. It goes, and then it goes to the mass spectrometer. And this is how the schematic of the mass spectrometer, this is how it looks like. So after the elemental analyzer, once the gases are produced and reduced, and the water is trapped, water vapor is trapped, it goes to the source, where the gases are ionized. Once the gases are ionized, they pass through a magnet. And once you know, any if you have learned some amount of physics, any charged molecules, when they pass through the magnet, they would be deviating from their path because they are charged, and we make sure that we singly ionize them. That is also another requirement here. So the heavier molecules and the lighter molecules, their deviation would be different. The heavier molecules will deviate a little bit. They have a high radius of curvature. The lighter molecules will have a low radius of curvature, and again this depends on their mass. And for example, in case of CO2, so although we want to measure carbon isotopic composition, we want to measure the organic carbon in the particulate matter that we have taken, but ultimately we have produced the CO2 gas, and we will measure them in the form of CO2. So the CO2, the major molecules having mass can be mass 44, 45, 46. So these will be ionized here, and they will pass through the magnet here. So in this quite a lot, and the deviation again they will be collected in different cups, Faraday cups mostly, where they will generate the current, and this current will be proportional to their abundance. So this is how we do it. Higher the current that is generated, higher will be the abundance of that isotopic molecules or isotopologues. So mass 44, 45, 46. So because we need to separate them, so this is how they are separated to measure their abundance. And again, this is mostly repetition of that, so I can skip it here. And this is what happens. They are collected here. And again, to measure the uh, isotopic ratio of 44 by 40, 45 by 44. Rather, we want in terms of 13C by 12C, but that can be converted back. So I will come to that conversion. But before that, how does this deflection work? So if you remember from your high school days, the Lorentz law, and any applied magnetic field, there will be some Lorentz force, and that Lorentz force will be equivalent to the centripetal force that is applied on, or that is working on those isotopic molecules, and they will be equal to each other. And if I do the balancing of this equation, then the radius of curvature that I get will be proportional to the mass, because the charge is remains the same, the magnetic field is the same, they are all singly ionized, and then depending on their mass, the radius of curvature would be different. So the higher the mass, higher would be the radius of curvature. And this is how the profile in the mass spectrometer looks like. So because the mass 44 is likely to have, not likely, but rather this is the case that it has the higher abundance, so it will have a higher peak, also a broad peak, and mass 45, mass 46, and this area under the curve will give me the abundance of these isotopic molecules. But again, like we need to convert this 44, 45, 46 to in the form of carbon 13 and carbon 12. So for this, there is something called Craig correction. He's the one who gave this correction for the first time. So in his name, in the name of Hermann Craig, who pioneered the stable isotope techniques, this correction is given by him. And this can easily, with the mass balance and with the abundance of isotopes that we know, it can be easily done. So for example, if we take the, let us say, alpha and 1 minus alpha, so if abundance of carbon 12 is alpha, the other one is will be 1 minus alpha, because the total has to be 100%. So let alpha and 1 minus alpha be the fractional abundances of 12C and 13C, and beta, gamma, and if for oxygen, if we decide beta is the abundance of 16O and gamma is the abundance of 17O, then 18O by definition or by mathematics, it would have 1 minus beta minus gamma abundance. So keeping these abundances in mind, we can form the CO2. So for example, if we take just O2, so O2 can be formed by 1616O, the abundance will be beta square. It can be 1617O, 1618O, and because it can be also 1716O, so the degeneracy will be twice. So it will be 2 beta gamma, and 2 will be here in case of 1717, it will be gamma square. So all this calculation I am presenting here, we cannot go in because of the lack of time. We cannot go into the nitty-gritty and details in these systematics. However, I just want to tell that with the mass balance, we can convert this ratio of 45 to 44 for 13C by 12C and 17O by 16O or 18O by 16O, this can be converted back. Now that is not the job done, because ultimately we want to do the rate measurements. So from the having measured the isotopic abundance in the particulate organic carbon of the incubated samples, how do we know that the how much is the carbon fixation or nitrogen fixation or primary production? So for that, we need to have a time parameter. And again, for time, we did the incubation. So we also take one sample at the beginning of the experiment. So that gives us the T is equal to 0 concentration and T is equal to 0 of isotopic composition. And then we analyze this. So again, the mass balance is also used here. So the ultimately that the mass isotopic, so here we are doing the isotopic mass balance. So the number of 15N atoms or the number of 13N atoms in a bottle that we are trying to balance here. So the mass balance equation would look like AF multiplied by CF equals to A0 into C0 plus AD into delta C, where the AF is the atom percent of 13 carbon or 15 carbon, whichever we want to take in the particulate phase after the incubation. So this one F means final after the incubation. A0 means atom percent of these isotopes at the beginning of the experiment. AD is quite interesting. It is the amount of isotope that is present in the dissolved phase. So once we have added the tracer, how much is available? So that should be after addition of the tracer. Phytoplankton may not be taking everything, but this is the food this is the isotopic food that is available to them. So this is what is AD. And then the C are nothing but the concentrations. So if we multiply the isotopic abundance by the concentrations, we get the mass balance of the isotopes. And after rearranging all this, we can get delta C by delta T. So the amount of time that we have incubated if we have incubated to 24 hours, we can divide this whole thing by 24 hours to get the uh, carbon fixation or nitrogen fixation. And the information that we are using, if you look carefully here, ultimately we got rid of a lot of terms. Ultimately we are using the isotopic abundances. And again, this goes back to my initial talk, where I described the isotopic changes are very small, but we are able to trace them with the IRMS that we use. We are able to trace them up to per mil level. So that means these terms we are able to measure very precisely. Likewise, the CF, the concentration also we are able to measure very precisely. And this is the reason the one of the most precise carbon or nitrogen fixation rates that they come from the isotopic tracer techniques or the isotopic incubation tracer techniques, if you would like to call it. And again, just to reiterate the assumptions that we have made, that there is a single carbon and nitrogen source for the phytoplankton. So when we add nitrate, let us say we say there is no other source of nitrogen in there. And there is no excretion of carbon or nitrogen by phytoplankton, because if there is a lot of excretion, then we will underestimate the rates quite a lot. But normally we say that the rates that we measure, they are not gross rates, rather they are net rates. So somewhere in those terms, it is fine. And then the isotopic discrimination is negligible. That means there is no isotopic fractionation. That means the biology does not prefer one isotope over the other isotope. And the 15N or the 13C atom percent in the dissolved phase is remain constant. It does not change with time. So this is about the isotopic tracer technique to estimate these rates. However, I must tell you that in last 20 years, almost the uses of nanosim. So this is not IRMS, this is nanosecondary ion mass spectrometry, which is quite different. It has kind of revolutionized the biogeochemical understanding, particularly of these different processes. So until now, what I discuss is that we were looking at the bulk nitrogen or bulk carbon, right? Bulk organic nitrogen, bulk uh, organic nitrogen and carbon. So that does not give us any idea about what kind of species are fixing it. whether this is you have a big community, all kind of phytoplankton are there, which one are taking more, which one are taking less. That kind of information we do not have. Also, if there is degradation or some other intermittent processes are happening, which do happen in nature, we do not get any idea. But with the help of nanosims, even within a single cell, we can track these different processes. So again, these are complement to each other. This is by no means to say that the IRMS or the bulk tracer techniques are not useful. Actually, they are the only way, or in terms of isotopes, to measure carbon fixation and nitrogen fixation. But if you want to look carefully within a cell, what is happening, or within different kind of cells, what kind of activities are going on, then nanosims is a way to look. So for example, if you look CO2 fixation within nodularia or within different species, or N2 fixation, or even dissolved inorganic phosphorus uptake, or the phosphorus content within a cell, we can track that how uh, much enrichment of these isotope happen when we do these tracer experiment, or even otherwise in terms in nature, how does it happen. So this is, for example, giving us 13C by 12C ratio. This is 15N by 14N, and that is why these numbers look very different. With delta units it will be very different, but here it is shown in terms of absolute ratio. So the red means higher, blue means lower, which is normally the the convention that we normally use anyway. So this is another way to trace different processes within a single cell for the better understanding of the biogeochemistry. So this one part of my talk is over, where I tried to explain you the estimation of or the calculation of uh, uh, different rates in the ocean. Now, if we want to naturally, if we want to see that what happens if we measure the isotopic composition of, let's say, zooplankton, or the isotopic composition of phytoplankton, or isotopic composition of nitrate, if we measure in the nature without disturbing them. In the previous cases, we have disturbed the system because we have added the tracer, we have added the isotope which was not abundant in the nature, but we have made it more abundant because we wanted to track the process. Here we naturally would like to see that how things span and can be still understand just by measuring the natural isotopic composition in different pools. So if we take the case of nitrogen cycle, in nitrogen cycle there are several processes. For example, here denitrification and anamox is listed here, which are the only two processes through which the ocean loses nitrogen, or ocean loses the bioavailable nitrogen. So this is denitrification, nitrite to nitrate, nitrate to nitrite to NO to nitrous oxide to N2, and then in anamox, the ammonium and nitrite, they join and they can become N2. So once it becomes N2, it is not bioavailable anymore. And this happens mostly in the anaerobic conditions, so mostly in the oxygen minimum zones. And again, these processes are also uh, in these processes there is a fractionation that happen, because there is one isotope is preferred over the other isotopes, and we, as we have learned, it is mostly the lighter isotope that would be preferred one over the other. So if we want to estimate these processes, denitrification and anamox, it can also be done with this systematic, like we did for N2 fixation or carbon fixation. We can instead of labeling with the bicarbonate or 15N2, we can label these oxygen minimum zone samples with ammonium or nitrite, because that is the substrate here. And we do this experiment, we measure this production of gases, because here the production would not be the particulate organic nitrogen. The production will be the N2 gas, and then the N2 gas can be 28 N2, so 14 nitrogen, 14 nitrogen, or it can be 29 N2, so 14 nitrogen. And if you want to add some tracer, it can be 15 nitrite, then it will be 29 N2. But that will be only in case of anamox, because in the anamox, ammonium and nitrite both are needed for, and this D stands for denitrification, A stands for anamox, and then there can also be production of 30N2. but the 30 N2 production will only be because of the denitrification, because in the NMOX you also want nitrite, and nitrite is not available in form of uh, there. So this is how, and again, all this mass balance, I'm just flashing it because I know these slides will be available on YouTube, so you can see them later on and pose me the questions. I will be happy to describe. But again, the similar kind of mass balance equations can be derived to estimate the NMOX and denitrification rates in the oxygen minimum zones of the ocean, and not just the oxygen minimum zones of the oceans. These techniques are actually also useful for terrestrial systems or aquatic systems or any other systems wherever nitrogen or carbon is being transformed. And in terms of source identification, like I said, we can use this concept of isotopic fractionation in there. So in nature also, in nature, these isotope fractionate fractionate in any process. So for example, the atmospheric nitrogen, if I start from here, by definition, the delta 15N of atmospheric nitrogen is 0 per mil, because the reference is the same. So the numerator and denominator, they are the same. So it is 0 per mil. And it, because it is highly abundant, 78% it is in the atmosphere. It also gets dissolved in the water. And there also the abundance is, the concentration of N2 is very high. Of course, it is not 78 because the CO2 takes over because of the carbonate chemistry of the ocean, but still it is very high. So the delta 15N is still very close to 0 per mil. When N2 fixation happens, then there is a small amount of fractionation, and that fractionation is of the order of 2 per mil. So this is called the, there are two kind of fractionations, kinetic fractionation and equilibrium fractionation. At times we assume equilibrium fractionation to be everywhere. That means the fractionation factor, which is defined by epsilon here, it remains constant. But however, in kinetic, it does not happen. So at times we just assume to understand different processes. So the particulate nitrogen that is produced by the N2 fixation would still be close to 0 per mil, because the fractionation is low. And then this can again recycled, this particulate nitrogen, this would become ammonia. There will be again some 3 per mil of fractionation here. There can also be a production of dissolved organic nitrogen, which will again have very close to 4 per mil fractionation here. So there will be some from 0.6 to we have gone here to 4 per mil kind of isotopic nitrogen isotopic composition here. And again, in the, if we go in the thermocline or deeper waters where nitrate is there, and there the nitrate can have the isotopic composition of 5 per mil. But in the oxygen minimum zone waters where there is denitrification, there is a heavy or the higher degree of fractionation that goes of the order of 15 to 25 per mil. So that is quite high compared to any of these numbers if you see. So that means the bacteria which denitrify nitrate, they prefer 14 nitrate over 15 nitrate, and they completely changes the isotopic composition of nitrate there. And if this nitrate is upwelled to the ocean waters or to the photic zone, and if this is utilized by the phytoplankton, and if we measure the natural isotopic composition of particulate organic matter, we can tell whether the nitrate was denitrified or it was not denitrified. Of course, there will be some other assumptions involved in there, but in a nutshell, I wanted to give you a broad idea that the isotopes are also, like in the beginning I said, they are also the fingerprints. So if we measure the isotopic composition in different nitrogen or carbon reservoirs within the ocean, we get a very good idea about the processes that happen. And also this can be applied to the past oceanic conditions. If we measure the isotopic composition of the foraminifera present or the forum bounded organic nitrogen, if we measure, then we can tell about the past whether denitrification was the dominant process or N2 fixation was the dominant process. So that kind of information we can also get. And if we measure within the species, then also we get the different delta 15N values. For example, in trichodesmium, which are the N2 fixers, their isotopic composition would be very close to 0 per mil because they fix N2. The Prochlorococcus, Synechococcus, depending on the conditions, their isotopic composition can be slightly different because they would utilize nitrate. If they were utilizing nitrate or ammonium from the oxygen minimum zones or the water which got upwelled in the oxygen minimum zones, their isotopic composition can even be a bit higher because of the denitrification. And this is my last slide. And here, so although this was more of a teaching kind of a talk here, not much about the science that we discussed or I mean, in terms of techniques, we did understand, we did try to understand where the subject or where the techniques they do stand as of now. However, going into the future of marine biogeochemistry, or also there has been already an application of compound specific isotopes. So going the beyond bulk isotopes, these isotopes are being used as a biomarkers or these compound because in this talk we have not learned anything about the dissolved organic carbon, which is also an important carbon pool in the ocean. So to better understand the dissolved organic pool, we do need these kind of techniques in there, and also we need to integrate these isotopic approaches in there. We can have high resolution techniques. There is also a need to have the multiple isotope systematics because at times we assume one set of processes, and if these processes are very different, then probably if we have a different isotopes, so we can independently validate whether how our assumptions hold to understand those processes. And of course we would like to go from observational scales to prediction scales. So I don't have a slides, but also you can learn more about the future scope about a program which will be soon endorsed by SCOR. The program is called BioGeo Escapes. And there we will be trying to understand, we will be going from observations to prediction of these rates. At the same time, there will be recommendation of the techniques that we would like to use. As you know, there can be different kind of techniques, but how these techniques should be used, what protocols should be followed, because we have to have a very similar or same protocols to compare our measurements in different regions. So for those purposes, we need to be there. So you can have a look more about the BioGeoScapes program. And with this, I would like to stop here. Thank you very much. Thank you for your patience.